Welcome to week 8 of chemistry tutoring. Today we will be talking about rate laws, as well as some of these rate reaction equations and some of these concepts that we will be covering of how things change and things like that. So let's get started right into it. We will be starting on question 13, and this is chapter 12 of your chemistry OpenStax textbook online. As always, let me know if you want me to link it below, and we will be recording these videos, these streams on Twitch and posting it to YouTube, so if you want to listen back to this at all, go ahead and do so. Other than that, let's get started. So, question 13. It says doubling the concentration of a reactant increases the rate of a reaction 4 times. With this knowledge, answer the following questions. What is the order of the reaction with respect to that reactant? Okay, so from this question, we should start with this equation that we'll be working from, and the equation is the rate equals K, and then A raised to the power of m, and then b raised to the power of n. So what all of this means is the k is a constant here. The a and the b are concentrations of a molecule or atom or anything like that. And then the m and the n are the order numbers. And so the order number in the chemical reaction, if we have like 2H2O, I'm just coming up with this right now, plus O2 gas. And it goes to, whatever. The order number is simply the coefficient that is in front of the molecule. So that's how you know the order number from the chemical reaction. But in this problem, it's asking for the order number of this reaction since it doubled. Or doubling the concentration increases the rate by 4. So if you were to look at this equation that we just took, right? If it was A, for example, and instead of A to the power of m, it's 2A to the power of m. And then it doubled. So let's just say A to the m is 1, right? And then 2 to the m is 4. So what just happened? So you could say that for right now, that since it doubled, it has to have a power of 2 here. Because if A, for example, is like a 1, like the answer to this one is A equals 1, right? Then doubling it will be 2A, so 2 times 1. And then the m has to be a certain number. That's the order number. So 2 to whatever power equals 4. 2 squared is 4. So this has to have a order number of 2 for this to work, because doubling the concentration increases the reaction by 4. So it has to be squared in that case. So the order number is 2. And so that's the answer. Okay, let's move on to B. And now it says tripling the concentration of a different reactant increases the rate of a reaction 3 times. What is the order of the reaction with respect to that reactant? So this one is similar. Let me move this right here. That's fine. Okay. So this one is very similar to the last one, but not quite the same. So since we are tripling the reactant and the reaction is tripled, it means this has a 1-to-1 ratio, because if this was to the second power, an order number of 2, so for example, if this had a power of 2, then the 3 would be squared, and we're just having A equals 1 in this case, and 3 was squared, then this would have 9A, so 9 times 1 equals 9, right? But in this case, if it was to the first power, to the first order, then it would be 3A to the first order, so 1 exponent power. Then it would be 3A, and then it would be 3 times 1, since we're having A as 1 here. and it'll equal 3. So in the second case here, it is tripling the rate, but on the left, it is multiplying it by 9. So it must have a first power because of this relationship. So the order number here equals 1. Okay, now let's move on to 14. So it says tripling the concentration of a reactant increases the rate of a reaction 9-fold. With this knowledge, answer the following questions. What is the order of the reaction with respect to that reactant? So tripling. So just as we did last time, like this problem right here that we just wrote out, or this example, in this case we are also tripling the reactant, or the concentration of the reactant, but it is changing by 9 times. And so that is what we got when it was to the second power, or second power order number 2. So that is the answer for this because it is being squared, so 3 squared is 9. So it is the order number of 2. So second order. Now let's move on to B. Increasing the concentration of a reactant by a factor of 4 increases the rate of a reaction 4-fold. What is the order of the reaction with respect to that reactant? So just as we were talking about with tripling the reactant, increased it by 3 times, this is the case of quadrupling it, and it increases by 4 times. So it's a 1-to-1 ratio. Nothing is being squared. It's just being raised to the power of 1. So the order number is 1. So first order. Okay. Okay, let's move on to 19. This is the rate constant for the radioactive decay of carbon. I believe this is supposed to say carbon-14. Carbon-14 is 1.21 times 10 to the negative 4th per year. The products of the decay are nitrogen atoms and electrons. What is the instantaneous rate of production of nitrogen atoms in a sample with carbon-14 content of 6.5 times 10 to the negative 9 molarity? So, using the equation that we've been talking about, and I'll write that again. So the rate, or I already wrote it right here actually. So the rate equals the K constant times the concentration of the carbon. And so since it gave us the K constant, so it gave us the K constant as well as the concentration. So, and it is, I believe, the first order because it's not raised, there's no coefficient with it. It's just carbon, it decays to nitrogen and then plus the particle at the end. So it is to the first order, so there's no exponent. So all we have to do is just plug and chug. And the K constant that we have here is 1.21. So it's this value right here that it gives, because it says the rate constant. 1.2 times 10 to the negative 4. And then the concentration is right here. It gives us the molarity. So that's 6.5 times 10 to the negative 9. And so multiplying that out will give us 7.865 times 10 to the negative 13. It actually, I made a mistake here. So it's not rate, it's actually nitrogen atoms. Nitrogen atoms. Because the problem was asking what is the instantaneous rate of production of nitrogen atoms. So it's actually the amount of atoms that is produced from this rate of production. Okay, let's move on to the next problem. Let me know if you have any questions, as always. I'll leave up that last part there if you want us to look at that. So 25 says nitrogen monoxide reacts with chlorine according to the equation. 2 nitrogen monoxide plus chlorine gas equals NaOCl. The following initial rates of reaction have been observed for certain reactant concentrations. So this one is very similar to what we just did. It's using that same equation. So, and it also says what is the rate law that describes the rates dependence on the concentrations of nitrogen monoxide and chlorine gas. What is the rate constant? What are the orders with respect to each reactant? Okay, so the first question is what rate law describes this. So the rate law is the equation we've been using. So it's rate equals the K constant times the concentration of one reactant multiplied by the concentration of another. And so that is the rate law that we are using that describes the dependence on the concentrations. And now it asks what is the rate constant and the orders respect to the constant. So we can answer the last question there. So what are the orders respect to the reactant? If we look back at this equation, or the reaction here, it's 2 NO gas plus 1 chlorine gas. So if you can see here, the coefficients in front of the nitrogen monoxide and the chlorine gas is 2 and 1. So the order numbers of the nitrogen monoxide is 2. So rewriting the last problem here, or the rate reaction, so the rate will equal the K constant times the concentration of the NO. And since it has a coefficient of 2, it'll have the order number of 2, and then multiplied by the concentration of the chlorine gas. And it had a first order, so it'll have an exponent of 1. So that is the rate reaction of this specific equation. Okay, so now it asks what is the rate constant. So in this problem, in this table specifically, it gives us the molarity, and then the rate. And so when we look at this formula that we have the rate that it gave us, and the concentration and the concentration. So, and it's asking for the rate constant, which is this K right here. So all we have to do is just algebraically move to solve for K, and then plug in one of these samples. So we will get the same exact rate constant for each of these. So for this reaction, it's going to have the same K. For this one, it's going to have the same K. And for this one, it will have the same K because the K is constant. It's not changing. So you can just take a sampler of just these values, and that'll work just fine. So let's algebraically solve for K. So let's move everything. So K will be on the left. And if we move these concentrations and divide it from the rate, we will get the K. So the rate divided by NO 2Cl2 to the first power. Okay, so I'm going to pull from the first sampler. I called it A right here, this one. So for the concentration, it's going to be 0.5 on the bottom squared, and then one of these is going to be to the first power, so 0.5 to the first, and the rate reaction is 1.14. Okay, and so when we solve all of that out, we will get a value of 9.1. And for the units specifically, it's going to always be liters squared divided by moles squared, and then whatever time unit it's in. Since we were used, since it gave the rate right over here in moles per liter per hour, for the rate it's going to be in hours. So the units of the K constant will be in hours here. So it's always going to be liters squared, mole squared, and then the time unit right here. So that is the answer for the K constant. And just to clarify, for the NO, it had a second order, and then for the chlorine gas, it had a first order. Just to clarify. Okay, let me know if you have any questions on that one. Let's move on to 26, if not. So 26 looks like it might be the same as what we just did. So this one says hydrogen reacts with nitrogen monoxide to form dinitrogen monoxide, laughing gas, according to the equation H2 plus 2NO, N2O, H2O. Determine the rate law, the rate constant, and the orders with respect to each reactant from the following data. Okay, so let's write down the rate equation first. So the rate equals the K constant times the concentration of one of the reactants. So one of them is going to be the H2. And I'm going to leave the exponent blank for now because we will figure out what the order number is. And then times the concentration of the NO. Okay, and as far as the order numbers go, from this reaction here, we can see that there is no coefficient. I'll write it down again. So it's the H2 plus 2NO. So we can see that there is a 1 in front of the coefficient and then a 2 here. So a 1 and then a 2 for these reactants. So that will be the order numbers. So the H2 gas will have a exponent of 2, and then the NO gas will have an exponent of 2, or 1 and then 2. Okay, and now it's asking not only the order number, but also the rate constant. And just as last time, this is the rate law, this equation for solving the rate. So now let's algebraically divide some of these variables, and so then we'll be solving only for k because we're wanting to find the constant. So it'll be the rate divided by the H2 concentration and then the NO concentration. And so I'm going to pick one of these columns for this data. I'll pick this one. So it'll look like this, the rate on the top, and it's in per second instead of hour. So just keep that in mind, that's the time unit. So we will have a value of 2.835 times 10 to the negative third for the rate, divided by the concentration of H2 gas, which is the 0.35, and then the 0.3 for the nitrogen monoxide squared. And so multiplying that out and dividing all of that, we will get a value of 0.09. And since the rate is moles per liters per second, we will have a unit value of K to be liters squared, moles squared, as usual, multiplied by the second. So that will be the value for the K constant. So now let's move on to 29. Let me know if you have any questions. So 29 says the rate constant for the first order decomposition at 45 degrees Celsius of dinitrogen pentoxide N2O5 dissolved in chloroform CHCl3 is 6.2 times 10 to the negative 4 per minute. That is the reaction right there. It's the 2N2O5 goes to 4NO2 plus O2. What is the rate of the reaction when N2O5 is 0.4 molarity? So, since we are only working with one reactant here, our equation is going to be the rate equals the K constant times the N2O5 And since it's 2 and 205, it'll have a second order, so it will be raised to the power of 2. And it gave us the value of the K constant, which is this number right here. So that'll be the 6.2 times 10 to the negative 4 and multiplied by the concentration, 0.4, and that is going to be squared. So then when you multiply all of that out, we will get an answer of 2.48 times 10 to the negative 4 per minute, or molarity per minute. And also, just to clarify, this should have had a, for the K constant, no, I believe this is the right unit. Yeah, so that is the answer for this rate. I was just looking at this, if this had correct units in the problem, but it does. Okay, so now let's move on to 40. We're going to skip 32 today. Okay, so 40 says, the reaction of compound A to give compounds C and D was to be found a second order in A. The rate constant for the reaction was determined to be 2.42 liters per mole square, or mole seconds. If the initial concentration is 0.5 moles per liter, what is the value of T1 half? So this equation that we will be working with is a little bit different than the standard rate equals K constant times the concentration to whatever power and concentration to whatever power. This equation will be specific to a second order reaction. Second order reaction. And so the equation will look like this. So 1 over AT equals KT plus 1 over A naught concentration. Oh, sorry, this was going on the outside. So that is the equation we are working with for this. And the AT, in this case, is going to be the concentration of whatever specific time. So that's what this T means. It means a concentration at excuse me, a concentration at any specific time. And the A naught here is the concentration at the initial start. And for the K, it's also going to be the constant, and then the T is going to be the time, the amount of seconds or hours, depending on the time units here. So for this this problem specifically, it is asking for what value at T1 half. So it is asking for the amount of seconds. So we will need to rearrange this equation to solve for T, solve for the amount of seconds specifically. So let's do that. I can just jump to it right away, but I'll show you what I do. So we have the 1 over AT here, and I'm just going to subtract this over there. I'm actually going to switch it, so when I'm solving, the K will be on the left. It's weird when what you're solving for is on the right. So the K is going to be on the the KT is going to be on the left, and I'm going to subtract the concentration from one another. Okay, and so now I can divide by K on both sides to isolate T. So it'll be 1 over that minus 1 over that divided by K. So that will be our equation that we are working with. So now all we have to do is just plug in the values that we were given. So for the 1 over AT, specifically it is asking for the value at T1 half. So when the concentration is half of what it started at. So it started at an initial concentration of 0.5 molarity. So at T1/2, the molarity will be 0.25. So I'll just write this on the left. AT is going to be 0.5 divided by 2, or specifically 1/2. And then the initial value of the concentration is going to be 0.5. There we go. So those are all of the values that we're plugging in. And then it gave us the K constant in the problem as 2.42. So now all we have to do is plug everything in. So it's going to be 1 divided by 0.25 here, minus 1 divided by 0.5, divided by 2.42. And when we divide and subtract everything, it will have a value of seconds of 0.826 as the t value. Seconds. So that is how you solve this problem. And also keep in mind that for 40, or this question, this had a second order in A. There's also a different equation for the first order when you're solving this kind of concentration at different time periods. So just keep that in mind. You'll be having to use a different equation altogether. So now let's move on to 49. Okay. In 49, I took it the long way, so we're going to skip this one for the sake of time. So let's move on to question 63, actually. Let me know if you do want to go over this. This has to do with what the partial pressure of this is, but for the sake of time, let's move on to 63. Okay, so 63 asks, the element cobalt exists in two oxidation states, cobalt 2 and cobalt 3, and the ions form many complexes. The rate at which one of these complexes of cobalt 3 was reduced by iron 2 in water was measured. Determine the activation energy of the reaction from the following data. So it's asking for the, I wonder where there was another question. It was removed. It's asking for the activation rate, or determine the activation energy. There it is. So from that, we need to figure out the equation that we are using. And so the equation for this, to solve for the activation energy, will look like this. So it's the natural log of K1 over K2 equals EA, and that's the activation energy symbol, divided by R times the difference in the changes of temperature. There we go. And from this, we can plug in these values and then solve for EA. And also keep in mind this R constant is going to be the same one that you've used before. It's the 0.08206 constant value, and we will get, because everything else works out with that constant, we don't have to change the pressure units at all within that. So let's solve for the EA, the activation energy, and isolate it so we can solve for it. So the activation energy is on the right again. I'm going to switch it over and put it on the left. So I'm just going to switch everything around. So swap the sides. So when I solve for it, it's going to be on the left. Okay, now I've swapped everything. And now I can multiply by R on both sides. And now I can divide by the differences in temperature. So divided by 1 over T2 minus 1 over T1. And this will equal the activation energy. Okay, so now we can plug in all those values it gave us. So going back to the table here, we will be using this as T1, and this is T2, this is K1, this is K2. You can always do the opposite and like have this as T1, or this the top one as T2, top one as K2. It doesn't matter, just as long as you're using the same temperature and K value for the same interval, and label it whatever you want. Just keep it together as the same variable, or the same, so they're both 1, and then the second one is going to be the 2, the T2 and the K2. But anyway, let's just plug in all those values, and our temperature is already in Kelvin, so that's great. And the K1 and K2 is great as well, so let's just plug everything in. Like I said, the R value is going to be 0.8206 natural log, and then the K1 we were given was 0.054, and then the K2 was 0.10, and divide everything by 1 over T2, which will minus 1 over T1, which is 293. And so when we divide all of that out, we will get a value of, 882.99316. And the activation energy is going to be in the units of joules per mole. And there we go. That is this entire problem. I'll zoom out. And there we go. Just from a little bit of tips going through these problems, it's always how I've wanted to kind of follow along with this material is figure out what you need to solve for, figure out if you have all the variables. If you don't, you might need to solve for some of them, for some of the unknowns first, before you can actually plug everything into the equation. So that's what I advise for everyone to do, and to figure out what equations you will be needing to start with. And then double checking sometimes on the side if the units check out. Like for example, the one that we did right up here. How we knew the K constant was that kind of value for the units. When I was solving for this problem, I made sure it made sense, so I can do that for you right now. So the rate was the mole per liter, and then the hour, and then the concentration was squared, so that's moles per liter, and that was squared, and then moles per liter. And so everything in the end was going to be moles times liters to the third power, and then divided by mole cubed, and then L, and then H. So everything checked out because the one of the liters canceled out, so it's going to be liter squared. This mole was canceled, so it's mole squared, and then H. So just things like that, just making sure that your units check out to whatever it's asking for, is really, really a good idea. But other than that, that is all that I have for you today. Let me leave up the last problem that we solved so you can look at that still. But yeah, that's been week 8. I will see you all next week if you don't have any questions. And as always, this posting will be uploaded to YouTube, and so you can always rewatch any of the streams that I do on any other of the weeks and any of the other chapters. So yeah, and good luck on next week, or good luck on your tests and maybe quizzes or anything that you have, assignments, and I will see you all on next Friday. And I will stick around as well.